Good morning. It's Prabchintan Randava from Austin, Texas. It's streaming the podcast last Saturday, so I thought I'll do another version of it this time. I also learned that when I mention the names of people, I don't like to pretend as if it's me talking the whole time, but it got cut off from the final stream last week. So I want to be clear that the combination that you're about to hear is the sitar is a lady called Rupa Panesar, and the voice is from Stephen Wolfram. He does these podcasts every week, live streams that offline I like to add some kind of music behind it. And so that's what I do, but it occurred to me that I should stream it so I could walk about and not be stuck to my computer, and I myself am the audience of the stream, so to speak. Um, I am making steak and eggs. That's the other thing I wanted to talk about, that I hadn't made them in a while, and I made them yesterday, and they turned out to be fantastic, except the smoke. I'm going for a medium rare steak and eggs, the classic, except I'm having a hard time nailing it down. So the mistake I made last time was I think I didn't heat my pan enough. The steak wasn't room temperature. My place got full with smoke. So this time I'm gonna do what's called a reverse sear, which means you put it in the oven first and then you do the cast iron pan bit later. So I'm gonna be doing that while listening to this, and I hope you enjoy and listen with me, whoever is listening in. All right, see you on the other side.
Hello, everyone. Welcome to another episode of Q&A about science and technology for kids and others. I think it's been a little while since I've done one of this particular type of live stream. So let's see what questions are saved up here. So a question here from Kathy. What's the difference between information and data? Is there a difference? It's an interesting question. People are often confused about this particular thing. So one of the things that is sort of a remarkable that we care about can be represented in a fairly uniform way. So images, sounds, text, each of those, as humans, we kind of consume them in different ways. Text, we read it with scanning word by word. Images, maybe there's some picture and we kind of might look around it in different places. Sound, we hear it with our ears and so on. These things kind of play differently to us as humans. But one of the big things that comes up with computers and computation and so on is that all those different sort of forms of human experience can be, in the end, turned into bits for a computer. So the ways they're turned into bits are different in those different cases. So, for example, for text, every letter, A through Z, whatever, every kind of character that you can put in a piece of text, every so-called glyph, that might be a letter, a number, it might be a Chinese character, it might be some mathematical symbol. All these kinds of things, there's a standard called Unicode that tells you, that probably is uppercase A, I think. For just the alphabet and ordinary numbers, there's a slightly simpler specification called ASCII that tells one how to take the 26 letters of the alphabet, upper and lower case, plus a bunch of other characters, and turns them into numbers between less than 128. when you're trying to represent kind of all the characters used by all the languages and so on of the world, the basic kind of collection of those is about 65,000 possibilities. And these days that's been extended because everybody needs emoji and things like this. And it's been extended to several times that number. But in any case, the main point is when you're dealing with text, every character in a piece of text can be converted to a number. And in the end, for the computer, you're converting that number to a series of bits. And you're doing that by saying, so in a base 10 number, number 127 or something, one's got, the 7 is in the units column, the 2 is in the tens column, being powers of, instead of being 1, 10, 100, 1,000, etc., it's 1, 2, 2 squared, which is 4, 2 cubed, which is 8, and so on. Each position represents a power of 2, and you can represent any number as 1 or 0 times each power of 2. And so you can convert any number into a sequence of ones and zeros. And that's ultimately how computers represent data in the memory of the computer. So, for example, in the case of a piece of text, what will happen is the text will be, in the general case, will be converted into a sequence of numbers that can be up to a few 100,000, and that sequence of numbers converts it into sort of raw data. Same kind of thing with images, like a typical image as recorded by a camera might be, 10 million pixels. So that would be let's say it's 16 million pixels, just because it's a convenient number, because then that means it's 4,000 pixels across by 4,000 pixels down, and each pixel represents a light level in that region of the image, a brightness of that region of the image, and then that brightness is broken into a red component, green component, blue component, because all colors can be represented as, all colors that we humans can see can be represented as more or less, at least, as a certain amount of red, a certain amount of green, a certain amount of blue. So once again, we're turning this image that we are used to perceiving as a bunch of different colors and light levels and so on in different places into a bit green and blue. And we might say it's, it's the red, green, and blue are intensities, and they're often represented using 24 bits each of to say what the intensity of red, green, and blue is. So anyway, bottom line, the image gets turned into a big 8 million numbers, and in terms of bits, it would be, oh boy, this is my math is failing me here. It's going to be about 48 million times. This is why I built tools that do math for one, is because I was never very good at doing this myself. But let's see, it's I'm trying to work out 16 times 3 is let's say 50 times 4 is 20 is 1,000. So that's 1,000 million bits, and that's 100 million as a pure representation with raw numbers. That would be, I think, 100 million bytes for that whole image. So for a typical piece of text, a page of text is perhaps let's see, maybe 20,000 characters. So that's a page of text is a much smaller number of bits of data to represent. So, you can go on and talk about other kinds of data like sound, for example. Typically, sound is a sequence of intensities that are sampled maybe 44,000 times a second. And so 44,000 times a second, you're giving a number that represents the actual intensity of the sound wave, and you're putting that together to represent sound as a sequence of numbers. So, okay, so you have all these different sources of input, and you can turn them all into sequences of bits. And that's kind of the raw data associated with each of those kinds of things, whether it's text, image, sound, whatever. The raw data is just that sequence of bits. Now, the fact is that all the details of that sequence of bits aren't. There is this particular pixel has, is 0.961 of red versus 0.952 of red or something. The human eye is barely able to distinguish that. And when it comes to, does it matter whether when we're looking at this image, does every pixel matter in the image? The answer is every pixel doesn't matter. I mean, if you made little changes to some of the pixels, the perception of the image would change not at all. And if you ask a question like, is there a cat or a dog in this image? You can change an awful lot of pixels and not change the answer to that question. So, when it comes to what is data, at the simplest level, its computer can represent. And the big surprise, the big interesting thing is that all these different forms of input can ultimately be turned into sequences of numbers that can be represented as bits in a computer. They all kind of turn into the same sort of thing. And you can measure, for example, how many bits it takes to represent, let's say, a piece of text, an image, whatever. The image will be slightly smaller than that in terms of sort of typical amounts of stuff that we might absorb in a second or something. In terms of text, the number of bits needed to represent it is much, much smaller than for an image or for sound. So then the question is, first question is, do you actually need to use that number of bits to represent kind of the content of what you're describing? And as I was saying, for images, a lot of the bits in that image are really quite redundant. You don't need them in detail. You could just take some much more kind of, those images are very rarely represented in their raw form as the actual color levels of every pixel. More often, they're represented in a compressed form. They're formats like JPEG and GIF and PNG, and then for videos, things like MP4 and so on. These are all ways of going from the raw collection of pixels with all their values down to something which is a much more compressed representation that contains the information that we need as humans to perceive that image, but it's not a faithful representation of what our digital camera recorded in every pixel. And so often that will be 100 times or even 1,000 times smaller number of bits needed than the raw number of bits that was needed. And how does that compression work? So for an image, a sort of typical thing that's done is to say, doesn't matter what every pixel value is, it only matters what the ways that those compression methods work. A very simple one is so-called ways that those compression methods work. A very simple one is so-called run length encoding, used to be used by fax machines back in the day, where what you do is you say, I've got a sequence of pixels. I'm gonna scan my image one line at a time, and I'm going to say, what's the sequence of pixel values as I scan the image? Well, if you were sending a fax, for example, that would be typically a black and white image of a piece of printed text or something, and there are large regions of that where it's just white pixel, white for a long time. So run length encoding works by saying, instead of giving every pixel value, you just say, I've got a run of 1,000 white pixels. So you're just saying 1,000 times a white pixel. Or you may have a little region of black for being the inside of a letter or something. It might be 10 black pixels. So that's an example of how you can compress the sort of raw data of that image, in that case of a piece of the original question was sort of the distinction between data and information. And ultimately the distinction is that data is kind of the raw representation of what, in terms of bits. That's kind of what one is talking about when one's talking about data. When one's talking about information, one is typically wanting to talk about the aspects of that matter to a human. So it doesn't matter what every pixel value is. What matters is the thing that you will perceive from the image. In the case of text, well, there's a certain amount of redundancy in text. So for example, typical thing you can do is if you have a piece of text, you can start just sort of blanking out letters, and you can say, can I still read this piece of text? And what you'll find for English is that on average you can blank out about half the letters in a piece of text. And if you kind of look at it real quickly and so on, you pretty much just read the original text as it was there. You wouldn't have to know, when you see the word elephant, practice when people store text for computers using formats like zip, for example, the gzip.gz and things like this, they often will do some compression on the text. And the compression, if it's just a generic piece of text, is usually about a factor of 2. The compression for images, where you only sort of care about what humans perceive, might be a factor of 1,000. The compression for audio, I think it's hundreds of times at least. And then, so that's kind of the compressed version is closer to what one might mean by information, by the thing that matters to humans coming out of what was given as input. Now, actually, one can go a lot further than that, because in the end, if the, let's see, what would be a good example? If you've got, if you know that you're going to be type thing, it's kind of like once you have the beginning of that and you're on a plane or something, you kind of know what the end of it is going to be. And in a sense, you could almost, it's kind of like telling jokes by numbers. You can be just saying, that's a number 3. And that could turn into a big, long description of, a Shaggy Dog story about the beaver crossing the road or something like this. Oh, that's just joke number 3. All I need to tell you is it's number 3. And all of that underlying raw data about what all the characters are going to be and all the words and so on and so on and so on. But I just have to tell you it's number 3. So when one thinks about sort of information and measuring sort of the quantity of information, one has to be sort of aware of the fact that there is, it's what matters is what you need to tell to a part of the sort of raw data that represented the thing that's being transmitted. So a very extreme version of this is when the thing you transmit is just a little tiny program, and the receiver is supposed to run that program, like on a computer, and see all the output it produces. And in fact, I've spent quite a bit of my life studying cases where you can run the program to generate huge sequences of bits and complicated patterns and all this kind of thing. That's a place where sort of the amount of true information that is being provided, it's just saying there's this little tiny program, but the amount of data that comes out from that can be very large. And another example of that is in something like math, where you can say the number pi. Okay, so in a sense, there's pi, the kind of, the word pi kind of gives you, so in some sense, an infinite amount of data about there's an infinite confusion around all of this, because sometimes people's meaning for these words is a bit different. There's this whole field called information theory that originated in the 1940s that had to do with kind of knowing, in part, how much compression you can make, given that you're trying to transmit this amount of data, how much can you compress that? And that depends on sort of how much redundancy is there in that data. How much do you not need to say because you can deduce it from the stuff you did say? That's one thing. Another piece of sort of information theory is when there's a certain amount of noise, when some of the bits you're trying to transmit don't come through the way you intended them to come through, how much can you then reconstruct? That's sort of the other big piece of information theory. And those are very related. But the fact is, you can usually reconstruct what they were saying. You can often reconstruct what they were saying. If you know kind of what you thought they were going to say, you have a much better chance to reconstruct what they were saying when there's a certain amount of noise. If they're telling you, names you've never heard before, and there's all kinds of background noise, you'll keep on saying, what did you say? What did you say? And so on. But if they're telling you things where really you only have to hear one word out of every three, because you kind of know roughly what they're saying, then you can withstand a quite high level of noise. Information theory gives you a sort of more mathematical way to talk about that phenomenon. But the thing about information theory is people often sort of say, well, information theory tells you how much true information there is in a message. It's not really correct, because the mathematical structure of information theory tends to be about particular ways of doing compression. It's a little confusing because the original sort of idea of information theory was to say sort of how to think about sort of what are all the possible messages you might receive. It's represented as bits, and then there's sort of the way of kind of joining up the data part of the representation of the message with the true information that's being transmitted. Which out of the 1,000 messages you might transmit, which one you actually transmit? Theory is that one is using particular ways of compressing and encoding the data. Usually you take a block of bits and you say, well, it's sort of redundant if we know that if it started 110, it's always going to continue 001. So we don't have to give the 001 at the end, we can just give the beginning. And there's this way of doing kind of block encoding, which lets you specify kind of a certain amount of compression. It's not all the compression, by saying, actually with pi, not very much at all, by saying what blocks of digits occur. You can't compress it very much at all because the digits of pi contain, its, so far as people guess, every possible block of digits appears somewhere in the digits of pi. We had a nice thing a few years ago about find your birthday in the digits of pi. That's possible because any sequence of digits appears somewhere in the digits of pi. Well, but nevertheless, when you're sort of counting amount of information, that means if you're just looking at digits from the outside with the context of what you're talking about, we just have to say pi, and that encodes an infinite amount of data, but also an infinite amount of information in the sense that people often use the term information in information theory, where you're talking about kind of compressing things by saying which blocks occur. So you can go a bit further and go to what's called algorithmic information theory, in which you're saying not, well, what blocks of digits occur, but what size of program do you need to reconstruct the data that you got. So in the case of pi, you need a fairly small program that's just a pi digit generating program that can go off, and if you run it for long enough, it'll generate all the, just keep generating digits of pi forever. So it seems like a really good idea, algorithmic information theory. So it seems like a really good idea as a way of capturing the true amount of information in something. How big was the smallest program you need to reproduce the thing? There's a bit of a bug though, because there's a question of, well, okay, you have a program. This is a sort of a deep problem in the theory of computation. The problem is, and it's like, is it going to generate what I want, or is it just going to flap around forever and just be in a loop and never come to a conclusion? The answer is, in general, you can't know. It's related to a phenomenon I've studied a lot that I call computational irreducibility. When you run a program, in general, you can't expect to jump ahead and say what that program will do. You're always, in the end, just going to loop like that forever. It's easy to jump ahead. But in general, you can't do that. And so algorithmic information theory, while it gives you, in principle, a way to say what's the true information content, the minimum program needed to specify this data, in practice, you won't, in general, be able to do that, because given if I give you this program and say, hey, I claim this program generates this data of that are kind of say, well, what's the smallest program that you only have to run for some number of steps that generates this piece of data? In general, it's the question of kind of how much true information is there in a thing depends very much on who is looking at the thing. What outside context do they have? What level of compression can they effectively do with whatever resources, whether it's sort of human brains or whether it's computer, whatever they have. So anyway, the sort of bottom line here is picking up that input, and information is more what is the true thing you need for a perceiver of that information to determine what is being said, either reconstruct the bits or get. Let's see. Oh boy, all right, to follow on from talking about bits. Okay, let me do two things here. So Klepto comments, does compression not have lossy and lossless versions? Yes, that is true. I was slightly eliding that point. Let me explain what that's about. So if you have an image, for example, you might have millions of pixels in the image. And when I was talking about run length encoding, where you say it's a sequence of white pixels, there's 1,000 white pixels, and then there's black pixels, and so on. Run length encoding, if you say there's 1,000 white, if you're given that the original pixels that you have, that's how, for example, to do lossless compression of images. Usually you don't need or want to do lossless compression of images because the details of every pixel don't matter. And so, for example, JPEG, PNG, GIF, they all do lossy compression of images, which means that you're just sort of keeping, okay. With specificity, what happens is in for example, JPEG, a typical thing that's done is you say, let's represent the image in terms of what are called Fourier components. And what that is you're saying across the image, it's like you imagine you have kind of a wave that goes, black to white, black to white, black to white. And that wave can be a very long wave, small wavelength, where it goes black, white, black, 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 white, every few pixels. The point is, you can represent the image by adding up this kind of, lazy long waves with very frenetic short waves. But to us humans, to our eyes, the details of all those frenetic short waves don't matter very much. The specific variation from doesn't really matter very much. So you can drop those very high frequency short wavelength pieces and you can just be left with the long, lazy, kind of slow variation kinds of things. And so in JPEG compression, what you typically are doing is to say, let's decompose the image into the kind of slowly changing big blobs of identical color and these very fast changing things. And in some places, like at edges, you might have to keep all the fast moving stuff, fast changing stuff, but most of the time you don't, where essentially you say, well, there are a certain number of words in the dictionary, and in some first approximation, the common words get short code words, like probably, something like, the word there or something, which has a bunch of letters, but it's pretty common, might get a very short code word. That might be word number 23. And the word elephant might be word number 4,000. You're trying to encode short words, more common words with short code words. And the idea is that's a lossless form of compression, because you can always go back and say, what was word 27 in the dictionary? Okay, it was this. It's exactly this. So that's and by the way, in the case of audio, it's typical. MP3, for example, does lossy compression. There are other kinds of files that do lossless compression, waves in air. And so what's happening is, the loudspeaker cone is moving and it's pushing the air and it's making a compression piece or whatever else. And the frequency of the sound depends on how fast the loudspeaker cone is going in and out. So for example, middle C on a piano is roughly 256 times per second of the loudspeaker cone going in and out. And so what's typically done is to sample sound 44,000 times a second. So that means, gosh, I have to do some math again. That's every 1/44th of a thousandth of a second. So that means if the loudspeaker cone is going in and out of what was the compression of the air in that time? What was the compression of the air in that time? 1,600 times. in a single loudspeaker cone wiggling to make a middle C note. But so what happens in sound, again, is most of the time, as in that middle C note, most of those 1600 samples, actually the way that, so that was, so that's why you can do compression. You can do lossy compression, because to our ears, it doesn't really matter whether you had, 50 different intensity. None of that is anything we could distinguish. So you can do compression for sound by using this kind of frequency idea, by saying what is the mix of frequencies, a little bit like what I described in the case of images. Actually, in the original case of MP3, the thing that was done was something a little bit more interesting and elaborate, which was, it was originally intended to be a compression method for dealing with human and the mouth and so on, and having our vocal cords vibrate and produce sounds. And in a sense, the kind of the set of sounds that can be produced by humans is determined by the kind of shapes, construction of their vocal tracts. They have syrinxes, and for example, they have the possibility of making, we have vocal cords that can sort of make one frequency of sound at a time, where more or less, whereas birds can make multiple ones, and so their kind of twitterings are somehow qualitatively different from human ones. And you can see that if you look at spectrograms of bird songs versus human speech. For human speech, we have these kind of dominant frequencies, so-called formants, that we make, where there's sort of a dominant frequency of the sound that we're making at every given moment in time. That frequency changes over time, and to say, well, wait a minute, you're making an E sound. Okay, if you're making an E sound, that's determined by the shape of your vocal tract. And there are not very many different numbers you have to specify to say it's a vocal tract with this shape rather than that shape. And so the idea was more or less to say, well, what were the numbers that you have to use to describe the human vocal tract to reproduce as a way to represent sounds. Ironically enough, even though it applied to music, where the sounds being generated are of a bit of a different character, but it turned out those methods worked well in that case as well. But so MP3 and so on is a lossy form of compression. When you're compressing videos, for example, with MP4, another big thing about videos is that from one frame to the next of the video might have a new frame every 60 times a second or something like this, or 30 times a second, but of it is much smaller because, among other things, from frame to frame, you don't have to store all the values of all the pixels in every frame. You can just sort of say, hey, this pixel is the same for 1,000 frames. Typically, and many changes that happen. Now, occasionally, you'll have situations where kind of lossy compression gets you into trouble. I've had that situation because I often generate these images that are computationally generated, where sort of every pixel is computed by a program and every pixel is different. If you have a photograph, usually the pixels have some smooth variation in most of the photograph. In the kinds of things I've often generated, it's like every pixel is a separate computation. And so if one tries to do lossy compression on that kind of image, you often get very terrible things happening, and you often get a lot of very weird effects that are perceivable to humans and aren't really anything to do with what's in the underlying image. But so lossy compression has this character that it's supposed to give you the stuff that matters to us humans and sort of ignores the stuff that doesn't matter. And the benefit of that is, by ignoring all that stuff, you get to compress the data a lot. Whereas lossless compression, you're supposed to be able to reproduce the original data perfectly when you receive it. So, well, let me just try and talk a little bit about that. So, one of the questions about when you have a computer and the computer's doing all these things with bits, and it might be doing sort of in the end, a modern computer is made of silicon and semiconductors and so on. A modern computer the CPU of a modern computer is billions of gates that there's a detail about whether it's current or voltage. Let's not worry about that. Basically, a little electrical signal comes in, and every gate has two inputs and one output. Two inputs come in. Each input is either there's a bit there or there isn't a bit there. It's either a 1 or a 0. And it's either a true, there's a bit there, or false, there's no bit there. And inside a computer, it's a very elaborate circuit that's made of a huge number, a billion or more, of these little NAND gates. And every NAND gate takes two inputs, gives one output. What does the NAND gate do? Let me explain a simpler case of an AND gate. An AND gate says, are both the inputs true, or 1, or on? Are both the inputs true or not? If both the inputs are true, then the output is going to be true as well. If either one or both of the inputs was not true, then the output will be false, 0. So that's what an AND gate does. It's kind of like, well, it's if you think about the inputs as 1 and 0, an AND gate is basically multiplying the two inputs together and giving the output. Okay, a NAND gate does the NOT version of that. So whenever the AND gate would have given a 0 as output, a NAND gate gives a 1 as output, and vice versa. So it just turns out that you can make any logical operation as a combination of NAND operations. So for instance, oh boy, can I do any of these? They get a little complicated. But basically a NAND of P and a P, and then a NAND of P comma NAND of Q comma R or something. But you can combine NANDs together to make ANDs and ORs and NOTs and any other logical operation you want to put together. And that's why those things are used as the raw material out of which you make computers and CPUs, is because by arranging those NANDs in all the right ways, you can make all the things you need in a CPU for adding numbers and multiplying numbers and jumping to this place and that place and so on. So, okay, that's the raw material of a computer is NAND gates. Well, one feature of NAND gates is they always have two inputs and one output. So we're talking a little bit about lossy and lossless compression and so on. One thing is, if you've got the input, you got, let's say, 2 bits of input, but you only have 1 bit of output. So there's no way you can uniquely reconstruct the input given the output. Because you could have, for example, in the case of let's say an AND gate, if you have 1, 0 as the input, it'll give 0. If you have 0, 1 as the input, it'll still give 0. So just knowing the output was 0 doesn't tell you whether the input was 1, 0, 0, 1, or 0, 0. Could be any of those three. If the output was 1, it so happens that for an AND gate, you then know that the input was 1, 1. But in general, you can't know. There's an ambiguity. On average, there's sort of twice as many things that could have been there in the input than you can know from the output. Okay, so that's the typical situation. Well, there's the question of, okay, when 2 bits coming in and only 2 input bits, think about it as the energy associated with those bundles of electrons coming in. Something has to happen to that energy in order for one to only have 1 bundle of electrons coming out. I'm cheating a little bit in the way I'm describing this, but let's go with this kind of way of talking about it for now. Well, what has to happen to get only 1 bundle out is you've got to dissipate half the energy associated with what came in. How do you dissipate energy? Well, you have to turn it, what was sort of electrical energy, you have to turn it into something that, that it's sort of a generic thing that can flow out of your computer. And that's basically heat. So what is originally sort of the organized bundle of electrons that represents one of those bits, as you dissipate the energy associated with that, it turns into just this incoherent bunch of little motions of the atoms inside your piece of silicon or whatever else. That's what heat. You're dissipating the heat associated with in if you go to a data center, for example, that has racks and racks of computers, you'll find there's an awful lot of heat being generated there. Usually a data center has these sort of cold aisles and hot aisles where all the computers are spewing their heat out into this hot aisle where it's quite hot compared to the other side, so to speak. And fancy data centers have all kinds of ways to get rid of that heat. It's one of the things that it seems very disappointing that all the power that's going into your computer, much of it is being dissipated as heat. And the reason that's happening is that you have this this phenomenon where you have to go from sort of two inputs to one output. You sort of got to get rid of the energy associated with one of those inputs. Actually, John von Neumann, a sort of pioneer of thinking about computers, just believed it was inevitably the case that every time you kind of did one of these gates, you would have to dissipate a certain amount of energy. And Rolf Landauer, who I knew, was the person who sort of codified that idea. But then it became clear that it wasn't actually necessary to dissipate heat and do computation. You could have it be the case that instead of having a NAND gate that has two inputs and one output, you could have a gate that had two inputs and two outputs, so that in principle, you could always go back from the output to the input. You didn't have to get rid of any energy. You could just have that in the output as well as the input. And the question is, was that practical? Because the problem is that often in a computation, you say, hey, I've got this question, it's going to turn into all these intermediate pieces of the computation. And in the end, I just want to know, is it yes or no? And somehow to get down to the is it yes or no, you have to get rid of all this extra bits and so on that you were preserving. You generate a lot of garbage bits and you throw the garbage bits away. Sort of the discarding of the garbage bits in some sense is going to dissipate heat. But you can perhaps do that in a more controlled way if you just, if you do most of the computation with all this back and forth going on in a way where you're never losing any bits. And then at the end, you've got a bunch of bits that are going to be the garbage bits and you dump them all at once. You can end up with a lot less heat being dissipated when you do it that way. Now, a place where this all got very relevant is in quantum computing. When you think about in the standard formalism of quantum mechanics assumes that no bits are lost, no information is lost. The standard formalism of quantum mechanics says that every gate that's happened reverse, you can always say, I've got the output, I can go back to the input. So in quantum mechanics and quantum computing and so on, one of the big problems is going from this, we're preserving all the bits, to I just want to know about the output and the specific one of these bits. That's usually called quantum measurement, and it's a big can of worms, which I actually think is not properly being thought about and hasn't been for a very long time. Actually, interestingly enough, John von Neumann was the person who also came up with the standard mathematical formalism that's used to think about quantum measurement and so on. But in any case, so quantum computing and thinking about quantum computing has made one more interested in this kind of idea of reversible computing where you can feed back the output and get the input back from it. Now, actually, there have been for many years sort of a trickle of attempts to be more serious about reversible computing. There's a company now called VAIR that I've been a bit involved with that is trying to make sort of a serious attempt of we're going to be able to fully reverse every computation, but they're kind of making use of sort of the energy that's being generated and used in every operation, so that sort of no energy has to be lost in doing the. I mean, one can certainly imagine a whole sort of programming language that's all reversible, and where you only sort of have to throw away the garbage at the end, and you could always reverse it at every step. There are all sorts of interesting reasons you might want to do that, in addition to the fact that you might be able to save lots of dissipation of heat. You might want it to be the case that you're doing a computation and you sort of speculatively try and do something and, oh, it didn't work out. Let's back it out of some kind. It does something you didn't want it to do. Imagine if you just say, well, I got to this state. Let me just literally back it out. We didn't have to explicitly store checkpoints of what the state of the thing was a little bit back. We could just say, given where I'm at, I'm just going to run the computation backwards and see where I get to. And so that's a place where you might want to do that. This is still of reversible computing. Let's see. Well, there's a comment here from Double saying they think data centers should be built alongside residential buildings so the waste heat can keep the homes heated. Okay, it gets more amusing than that. There's a company we had some interaction with, I think it's called Quano, and their business model was to provide heaters for residential buildings and particularly hotels, where the heater is a computer, and where the heating the hotel room is doing computation, and so yes, I mean that's a concept, and you can also say, you're saving money by having your heater double as a computer, and then you're selling the compute back to some kind of cloud provider as a way to get sort of a rebate on your heating costs. So yes, that's an interesting thing one could think about doing. In general, kind of data centers these days, they need a lot of electrical power, and they need to be able to dump the waste heat. And often, there's been a lot of sort of data centers near hydroelectric plants where electricity is cheap. There's lots of discussion about nuclear power for data centers and so on. I have to say, I think that in the 1950s, it's inevitable that computation XYZ must take a certain amount of energy, must dissipate a certain amount of heat. We know from the theoretical idea of reversible computing, that's a whole challenge of its own. Let's see. Well, let's go back to some earlier questions here. Patrick is asking, if I cloned my brain exactly, would the copy think it was me? I suppose we think of ourselves as ourselves, and even though we go to sleep and we're not kind of remembering every past instant, we wake up in the morning, we're used enough to going to sleep and waking up again that we kind of say, yeah, that's the same me as it was last night. That we have this kind of continuity of thinking it's us from the inside. Now, if you say, does the copy of me have that same continuity of thinking it's the same copy? It should be, yeah. It's going to have the same thinking that it's going to continue thinking it's the same the same quotes me that it was before. Now the question is, does the copy think that it's the same me as the original was? And I think the answer to that is really, in many senses, no. I'd like to be an identical twin because I'm not, but there's a certain sense in which assume, and it won't in fact be the case because of the way that brains form, brains of identical twins just like non-identical. But let's imagine even that they were. As soon as it is not the case that each twin has sort of a continuity of experience of I'm twin A, I'm twin B, and they have a continuity of experience within themselves. But I don't think there's a kind of, oh no, I'm actually twin B thinking I'm actually twin A. Now, confusingly, twin B might be able to say, I know what twin A is going to do next, because I can sort of run themselves in my brain, so to speak. When you think about, oh, what if I could upload my brain to some digital brain vault somewhere, mind vault somewhere, would the thing in the mind vault think it's me or not? If it, it's sort of an interesting question where it came from, and it had no ability to see the original me, then I suppose if you ask it, who are you? It's going to go back to its memory that came before the fork where there was a copy made, and it's going to respond, I am the original, because what else could it do? In the question of, do you wake up and now you're a digital you, what does that mean? Because it's the thing that you prevent it from having a knowledge of the fact that there was, what its origins were, and that there is that you that still exists, or maybe it doesn't. I think, boy, this is tangled, isn't it? The tangled story. It really depends on what it means to think it's me, and what it means to, it can think it is a definite existent being that if it knew nothing else, it will think it is just the continuity of the memories that came from it originally. I think that's probably the best one can say about that. Well, Charles is commenting, I think that the copied mind is like having the data without. There's a question of sort of how much you're copying the memory state as well as the machine that's running. Yeah, I mean, for sure, in the experiences of the world from two different minds will be different. Unless those minds are hooked up to the exact same sensory input, the experiences of those minds will be different. And so very quickly, the what's in one mind will differ from what's in the other mind. I think when it comes to, for example, neural net models and things, and you can do this kind of thing with those, there's enough kind of randomness that's used in the training of neural net models that sort of, even though you might have two neural nets with the exact same input, unless you very carefully lock down the kind of randomness that's typically used in training, you'll end up with two different arrangements of actual remembered stuff in the neural net. And so you'll end up with, again, not sort of identical behavior in the two neural nets. Let's see. From Pack, they're sort of assuming, insofar as cats see humans as bigger, dumber cats, how would robots see humans? Would they understand the difference, or would they just assume that we are dumber robots? It's a reasonable question. It's a question that goes to the core of a lot of the way that we perceive the world. I mean, the fact is, when people say there are, spirits of the forest, so to speak, there are things where sort of things are happening in the world that seem like they have minds associated with them, and they even seem like they have human-like minds. We tend to project onto, for example, things in the natural world, something which is like our inner experience of how that same kind of inner experience is merely an assumption. We can never get inside their minds to have that same inner experience. It's just like, oh, that's a person like me, therefore they must be having experiences like mine. Well, similarly, when we see things happen in nature, or we see animals do things, it is a natural thing to kind of project from our human feelings about how things get done, those same feelings onto how computers work. I mean, my computer is having a hard time with that. My computer is struggling. You can hear its fan running. Its CPU is running full out to do this particular computation. My computer is struggling. Well, that's sort of projecting a human-like characteristic onto the computer. And that's something that it is very much our model for the world, and that's certainly true in the sort of pre-scientific era. Our model for the world is much more, it's all human-like stuff going on in the world, even though in some sense it's really just nature and not mind-like or human mind-like stuff. So I think there is a natural tendency of at least minds like ours to project that there are also minds like ours in other things that do. And I don't know, that fish that house for a long time. It wants to kind of chill out and relax. Well, is that really the right description for the cat? That is a human impression projected onto a cat. Now, the truth is that cats probably have many of the same emotional states that humans do, probably because the actual that humans do. But that's again kind of a projection from us humans. So I think it is sort of a natural thing that any mind with particular inner experiences can have a theory about how other minds or other things work that is based on its inner experience. So yes, I think it's probably the case that in some sense about that. If we imagine a neural net that is trying to model sort of human behavior, how is it doing that? For example, let's say it's a tutoring bot that's trying to make a model for what the student understands and doesn't understand. It's doing that implicitly by having a representation in the neural net way of thinking inside the neural net that is kind of an approximation to the human way of thinking on the outside. So in some sense, it's inevitable that there's a representation in the thinking patterns of a neural net about what the thinking patterns of a human on the outside might be. All right, let's see, maybe one more question and then we should wrap for today. From Double. If I had a spaceship that had a device that could disable or decouple all of the Higgs bosons from all the particles of the spaceship, would the ship be able to travel at the speed of light? The answer to that is yes. And the only example, main example we know is photons, particles of light. It is an inevitable feature of things that have no mass that they travel at the speed of light. It's kind of almost tautological to say light travels at the speed of light. There are other particles that are massless, like gluons, but the story is a bit more complicated there because they're always stuck inside other particles. But anything that has no mass travels at the speed of light. That's almost a definitional point. So the thing is, how do things get mass? Well, in the standard model of particle physics, things get mass by every background Higgs field that fills the whole universe. It's a bit embarrassing because in the usual way that things are set up, that background Higgs field has so much energy and mass that it would curl the universe up into a tiny ball as a result of its gravity. Sort of in the traditional model of physics, that's one of the problems. But so the way that things get mass is they just keep on interacting with this Higgs field. It's like, I'm trying to just move at the speed of light. But no, I keep on getting a kick from this Higgs field that is sort of throughout the universe. And that series of kicks is making me not travel at the speed of light. It's kind of like when light goes into a medium like water or glass or something. What's happening is the photons of light keep on getting absorbed by an atom in the water, by a molecule in the water, then they get re-emitted. And it takes a little moment for the molecule in the water to say, oh, I absorbed a photon, wiggle, wiggle, wiggle. Eventually, I'm going to re-emit that photon. It's not quite the same thing in the Higgs mechanism for mass, but it's more that sort of covers the universe. Higgs particles are little wiggles in the Higgs field. It's kind of like saying the Higgs field is like your ocean. It's just a whole bunch of water. But then on the surface of the ocean, you can have a little, then, if you want to kind of send some signal across the ocean, you'd make a little wiggle and the wiggle would propagate as a wave. Higgs particles are those waves operating in this sort of ocean, Higgs ocean, that is the background Higgs field of the universe. So if you say, let me decouple everything from the Higgs field, from every interaction with Higgs stuff, then the answer is, if you could do that, you would have a thing that was massless. One issue with that is, if you've got your spaceship and your spaceship is hanging together, the spaceship sort of thingness has to have mass. If you have things are just going to go in different directions at the speed of light, and there's no longer sort of a thing that's there, not an unusual sense of a thing. I mean, you could have a whole bunch of photons that are all in some pattern. They're all traveling together, and I suppose you can imagine that as a little bit of a spaceship. Actually, one weird thing about that spaceship is, in no useful sense, you'd never be able to walk from one part of the spaceship to another and back again. It would just be, it's just like this projection of a spaceship that's just, all the pieces of the spaceship are just traveling at the speed of light. They're never interacting with each other. So that's what sort of happens if the spaceship is converted to something that's massless. And I have no idea how you would isolate yourself from the Higgs field, but that's what photons of massless particles. All right. Well, thanks for some interesting questions. Time for me to go to my day job. Actually, I think I'm doing a live stream design review in just a couple of minutes here. So thanks for joining me, and see you another time.